Alright, here we go with iChem lesson 29 on definitions of acids and bases. This is our second to last iChem lesson. Make sure you're taking notes and following along on your viewing guide. So first, you need to know the properties of acids and bases. Acids and bases both ionize or dissociate in water. We're going to talk about what that means in a minute. Acids taste sour while bases taste bitter. Acids conduct electricity, and so do bases, and this ties back into this idea. They conduct electricity because they ionize in water, which means they become, in the definitions of our solutions, electrolytes. Both of them cause indicators to change color. Now, they cause indicators to change different colors, which is how we tell them apart, but they both can cause color change in certain situations. The most important marker we're going to talk about, or most significant maybe, or actually maybe I should say the easiest marker for us to use is this litmus paper. You probably used it in some of your middle school science classes. Acids turn litmus paper red, and bases turn litmus paper blue. So B for base helps you remember blue, and then acids turn it red. Acids, and we know this already, react with metals to form hydrogen gas. This is our double replacement reactions, a lot of ones we've been doing over and over again. And a unique property of bases is when you feel them on your hands. You get like soap, for example, or laundry detergent are both bases. You get them on your hand, they tend to feel slipper, let's just say slippery with a Y. So, what does this idea of dissociate in water mean? To dissociate means to break apart into ions. So acids and bases dissociate in water is what we say. It means acids and bases break apart into ions in water. Dissociation reactions show this phenomenon in the form of a chemical equation. So we can write that hydrochloric acid dissociates into hydrogen and chlorine ions, one hydrogen and one chlorine. You can do calcium dissociates into one calcium and two hydroxide ions. This is familiar, it should be from colligative properties because we explored this idea. We're talking about salts and how we calculate the number of ions. Acids and bases do the same thing. But notice these arrows are reversible. Acid and base dissociations are reversible reactions, which means sometimes in solution, hydrogen and chlorine can recombine to make hydrochloric acid in solution. So acids are both ionic and covalent in solutions in some cases. Sometimes you have the covalent version around, and sometimes you have the ionic version around, dissociated into its ions. For the idea of strong and weak tells you kind of about the ratios of that. Strong and weak do not mean the same as concentrated and dilute. So you can have a dilute strong acid and you can have a concentrated weak acid. They're different ideas. So what does that mean? It's talking about the dissociation. So strong acids completely dissociate when dissolved in water. So hydrochloric acid is a strong acid. So that actually means not reversible. It completely dissociates all the hydrochloric acid, this hydrogen and chlorine ions. This will make our calculations in the future a little bit more useful. Weak acids are much harder in calculations, so we're not going to do a lot of calculations with them in this class. And they're harder because they partially dissociate when dissolving in water. And it's harder to tell exactly how many hydrogen ions you would have, for example, if you had a weak acid. So let's do a little bit more side-by-side comparison. Strong acids, there's only a few of them dissociate completely and remain dissociated. You want to have this list. So any of the acids that are formed with our halogens are called halides. HCl, HBr, and HI, hydrochloric, hydrobromic, and hydroiodidic are all strong acids. Now notice that HF, hydrofluoric, is not on this list. It is not a strong acid. So skip fluorine, and then the next three down. The reason why hydrofluoric is not a strong acid is because fluorine is so electronegative, it so strongly bonds to that hydrogen and doesn't want to let it go. So here's an example. If I add hydrochloric acid to water, it's going to dissociate completely into hydrogen ion and chlorine. A few other examples are our oxy acids, sulfuric acid, I just told you what it's called, hypochloric acid, and nitric acid all form strong acids as well. So completely dissociate. If I put them in water, they completely break up into their ions. We'll use these later during our the calculations in this unit, which will be our last and final iChem. The most acids, so all the other acids except for the ones that are listed there, also have the reversible reaction. So sometimes some of it exists in this non-dissociated form, and some of it exists this way. This reaction, it reaches what's called equilibrium. So for every one of these that reacts that way, another two are going to combine and go that way, and it's going to come and reach this kind of calm status in the middle, equilibrium. Okay, so our first definition of an acid is ones that are the Arrhenius definitions, and it's the definition we've had all along of an acid. It's a compound that produces hydrogen ions when dissolved in water. So if it has a hydrogen ion, it starts with an H, like hydrochloric acid. When dissolved in water, it produces a hydrogen ion and an anion. By definition, I start with an H here, I have a hydrogen ion here. This makes it an Arrhenius acid. We can also write this another way. Notice this water is here. Water is actually participating in this reaction. So often we write it this way. So hydrochloric acid plus H2O yields what's called the hydronium ion, H3O plus Cl minus. We're using this and this interchangeably here. Hydronium and hydrogen ion mean the same thing, because what a hydronium ion is, if you remember, water is polar, so I got my polar water right here, got my hydrogens, and they're slightly positive over here, and that makes my water with the lone pair slightly negative here. If I have a hydrogen ion floating around in solution, it's going to be attracted to this hydrogen, this negative oxygen here. So it's going to hang out real close to the water molecule. It's not a bond per se, but this forms what we call the hydronium ion. So the definition of a base, and you've probably seen these before, sodium hydroxide is the most common example we use. Anything with a hydroxide ion is considered an Arrhenius base. So an example, NaOH. Look at the end, if it has an OH at the end, that means it's a base. When you add it to water, it's going to form a positive ion and a hydroxide ion. The other definition, the Bronsted-Lowry definition, that takes a little bit more work to understand, is it an acid, base, and so on. Here, acid is defined as a hydrogen ion donor. Remember, hydrogen ion is H+. If we remember our structure of H+, we're just going to have one single proton, no electrons in anything around it. So hydrogen ion is the same thing as a proton. A single proton by itself is essentially a hydrogen ion. And a base is a hydrogen ion acceptor, so a proton acceptor. So acid is a donor, a base is an acceptor. So let's look at the example that you have on your paper. I have ammonium plus water reacts to form the ammonia ion, or I have this backwards, sorry. Ammonia reacts with water to form the ammonium ion and the hydroxide ion. Okay, doesn't start with an H, so it's not necessarily an acid by definition. It doesn't end in an OH, so by the other definition I can't say it's a base, but I can say either the ammonia donates a proton or accepts a proton. So let's follow the pairs. Nitrogen kind of is a bystander in this, so follow the nitrogen. Nitrogen is in here and in here. What happens when I go from here to here? Well, I add an H, right? I had 3 and now I have 4. If I add an H, I'm accepting. Okay. Adding the H is accepting. Draw the arrows on your paper. This is a confusing concept. You're going to want to have all this down. Now, let's follow our water. It should do the opposite, but let's just be sure. The H2O oxygen actually is our bystander in this because we're only talking about hydrogens changing place. So follow the oxygen. Well, I have 2 H's over here and now I have 1 H. I'm subtracting an H. That means I'm donating. Okay. So if I'm talking about which one's the acid and which one's the base, NH3 adds an H, becomes NH4. That makes it the acid. H2O donates or loses an H to become OH. That makes it a base. Okay. Now we talk about these ideas of conjugate base and conjugate acid. So remember, I called ammonium my base, and I called water my acid. The conjugate base is formed when form tells you it's a product. Formed when the acid donates a hydrogen ion. Okay, so I already identified this is my acid. What was formed when it donated is my conjugate base. And then, same definition, same idea, conjugate acid is formed when a base accepts the hydrogen ion. So here's my base, here's my base after it accepted the hydrogen ion, so this makes it my conjugate acid. The conjugates are the products to go with the pairs. So a conjugate acid pair are things that differ by only a single hydrogen. So NH3 and NH4, 1 hydrogen's difference, and H2O and OH, 1 hydrogen's difference. Let's do 2 more examples. This first one, I'm following my sulfate. It's a bystander. I'm just worried about hydrogen. So I have 2 hydrogens there, 1 hydrogen there. I lost a hydrogen. Minus a hydrogen donates a hydrogen. This makes this an acid. Water, follow the O. 1 hydrogen there, 3 hydrogens here. This is plus an H. That makes this the base. Well, the acid forms the conjugate base, and the base forms the conjugate acid. Let's do one more. I have HPO4 2 minus, follow the PO4. 1 H there, 2 H's there. I'm gaining an H. Gaining an H makes that a base. Accepting, gaining. Water, follow the O's. 2 hydrogens, 1 hydrogen. I lost a hydrogen. Losing is like donating. That's an acid. Now the pairs. Base forms a C acid. Acid forms a conjugate base. Notice water can be both an acid or a base based on the Brown-Sedlary definition. Draw your arrows, decide, adding an H or